Hello everyone, welcome to lecture 4 of the online course on modern display technologies, flat panel display. Today's lecture will be on overview of different flat display technologies. So this is a part 1. We'll also have some of the display technologies discussed in the next lecture. So in this particular lecture, we'll be mainly covering the 3 very popular flat panel displays like the LCDs, LEDs and OLEDs. So let's begin one by one. Okay. So flat panel displays, as we understood, they are characterized by their slim profile. Typically they are few centimeters or less, regardless of the screen size. So no matter how big is your display, the thickness of the display is typically fixed, it's few centimeters. So specifying a display or the design and the optimization of a display based product basically requires selection of an appropriate technology and are also strongly dependent on the application and the intended condition of the usage, right. So we understood from the last lecture that depending on the outdoor condition or the ambient condition for the display, a lot of things may change. So the rapid advancement of flat panel display has led to wide variety of display types and options. This progress highlights the need for product engineers to have a complete understanding about the different technologies. Typical examples can be used to illustrate the diverse range of available display options. For instance, the liquid crystal display, which is LCD, is presently the dominant flat panel display technology, and it is available with diagonal sizes that are ranging from less than 1 inch, that is the micro display, to over 100 inch. Okay. So you can understand that the range of this kind of displays. So let us focus onto the market leader currently in display technology, that is the liquid crystal display or LCD. Now the liquid crystal display is based on liquid crystal cells, okay, as they act as light modulator, because this kind of display or this liquid crystal cells do not emit light on their own. Okay. So what you have here, typically a CCFL or cold cathode fluorescent lamp is basically used here as the backlighting for the LCDs, and then you have 2 cross polarizer. So you see this is one polarizer which is 0 degree, so it actually allows the light with polarization, the vertical polarization can pass through. Okay. Then you have the liquid crystal, the twisted pneumatic liquid crystal. So twisted pneumatic liquid crystal allows the polarization of the light to get bent by 90 degrees, okay, because of the nature of this crystal. So when light propagates through this material, it the polarization axis gets rotated by 90 degrees, and then you again have another polarizer which is basically a horizontal polarizer or 90 degree polarizer. So this polarization can now pass through and you get a bright light. Now what happens when you employ some sort of voltage across that liquid crystal cell? Okay, this twisted structure is basically broken. So the polarization of the light will remain same. Okay, so this vertical polarization comes out here as well. Now this polarizer is a horizontal polarizer which will only allow the horizontal polarization. So what happens to this vertically polarized light? That gets blocked. So you get a complete dark. Okay. So this polarized light cannot pass through and you get a dark state. So you understand that in most LCDs, 2 cross polarizers are basically employed, which can provide a high contrast ratio. However, the use of polarizers basically limit the maximum optical transmission or transmittance to about 35 to 40%, okay, unless a different polarization conversion scheme is implemented. Moreover, at oblique angles, the optical performance of an LCD may degrade because of two main factors. The first one being projections of optic axis of the two cross polarizers onto the electric field vector of the light will no longer be perpendicular to each other. So, that basically complicates the maintenance of a good dark state over a wide viewing cone. So, the quality of your image will degrade. Second is the liquid crystal is a birefringent medium, means along two different axes it shows different refractive index. So, it is birefringent. Okay. So, the electro-optic effect that you see here depends on the relative direction of the incident light and also the arrangement of the liquid crystal in the cell. So, this works perfectly fine for one viewing angle, but when you go for wide viewing angles you will not be able to see very good contrast, and also you will not get uniform color rendering. So, these are some challenges. So, to achieve wide angle viewing, what people have done, multi-domain architecture and phase compensation films, okay, something like uniaxial or biaxial films are commonly employed. So, these films basically compensate for the light leakage that is caused by the cross polarizers at large incident angle, okay, and the birefringent nature of the liquid crystal layer. So, you need this extra phase compensation films to make the LCD workable at large viewing angles. So, using this phase compensation technique, transmissive multi-domain LCDs can exhibit high contrast ratio, high resolution, crisp image, vivid colors, and also a wide viewing angle. Okay. So, here is an example of a 2:16 alphanumeric LCD display, which I am sure all of you might have seen. Now, despite all these improvements, the displayed images from LCD can still appear washed out under a direct sunlight, which will basically affect the readability in high ambient light condition. So, here is an example of a LCD smartphone display under bright sunlight, and it is very difficult for you to basically see, because here you can understand that in the outdoor settings with clear weather, the reflected sunlight that is coming from the LCD surface is basically much brighter than the light that is being emitted by the LCD display itself. Okay. So, it will basically reduce the ambient contrast ratio. Now, in order to increase sunlight readability, you can think of applying broadband anti-reflection coatings, or you can do some adaptive brightness control, means whenever you have a camera that senses the ambient bright condition, accordingly when the ambience is bright, you basically draw more current and produce more bright light from your backlight source itself, so that the image itself is brighter. Now, reflective LCDs basically improve the sunlight readability by using ambient light to illuminate the displayed images. So, that basically eliminates the need for a backlight. Okay. So, typically when you use reflective LCDs, this result in reduced weight, thickness and power consumption, as also seen in applications something like in wristwatches. Okay. However, if you look into reflective LCDs, they generally offer lower contrast ratio, color saturation and viewing angle as compared to the transmissive LCDs. And obviously, in completely dark conditions, reflective LCDs are unreadable, limiting their application. So, what to do? You have to basically get the best of both. Okay. So, in order to overcome the sunlight readability issue while maintaining high image quality, a hybrid display termed as the transreflective LCD have been developed. That means, the same LCD module will have some transmissive display part, some reflective display part. It is kind of a hybrid. Okay. So, in a TR LCD, each pixel is basically subdivided into two subpixels which provide transmissive and reflective functions respectively, right? And the area ratio between transmissive and reflective can be adjusted depending on the application. So, for example, if the display is mostly used outdoors, then the design will have say 80% reflective based area and 20% transmissive based area. If it is mostly used indoors, you just swap the transmissive area to 80% and reflective area to 20%. Now, in a dark to normal ambient, the backlight is basically turned on and your trans-reflective LCD starts working as a transmissive display. And when you go under direct sunlight, this TR LCD will start working the reflective mode. Therefore, its dynamic range becomes very wide and its functionality no longer depends on the ambient lighting conditions. So, you basically can switch between the two modes, transmissive or reflective modes, based on the requirements. While trans-reflective LCDs enhance sunlight readability, their fabrication process is much more complex, and you can understand that their performance is somewhere in between the reflective and the transmissive LCDs. So, obviously, their performance is basically inferior to a regular transmissive displays. That is why the TR LCDs have not been widely adopted in commercial products, because when you use televisions, typically those are for indoor conditions, and we know the lighting modes, and we basically decide which type of LCD we will be using. So, today LCDs have found widespread usage in our day-to-day life, including the smartphones, tablets, virtual reality, augmented reality displays, the automotive displays, navigation system, computer notebooks, desktop monitors, and even the large screen TVs that you see for concerts and all. So, we will discuss LCDs going into much more details in the upcoming weeks. So, let us just have a quick overview of the other competing technologies for the flat panel display. The next comes is the light emitting diode based technology. So, light emitting diode, as you all know, is an electroluminescent device based on crystalline semiconductors. Okay. So, to convert electrical to optical power, one has to inject carriers into the LEDs through electrodes, which then recombine and gives us light. So, you can basically have LEDs of all these different colors. So, in other words, light emitting diodes are basically made from semiconductor p-n junction on a crystalline substrate, where electron hole recombination under forward bias condition produces light. I will not go into the LED basics, because I believe all of you know about this. Here we will be focusing on using LED for display purpose. So, the transmission wavelength of an LED is basically determined by the band gap of the semiconductor, and it can be fine tuned by the device design. So, the emission wavelength basically depends on the material, the active layer design, and the device structure. So, these are the current standards in LED manufacturing. Aluminum, gallium, indium phosphide are basically used for long wavelengths, something like red, orange and yellow LEDs. Gallium nitride, indium gallium nitride and aluminum gallium nitride, these are the key group 3 nitride semiconductors, which are popularly used for short wavelength LEDs, okay, as they can cover the spectrum from UV to blue and green. Okay. So, what LEDs have provided, that rather than providing a display itself, okay, an LED can also be used as a light source, such as in a backlight module for an LCD, which replaces the CCFLs, and it can also be used for general lighting. So, this is an important motivation to use LEDs in the LCD displays for replacing CCFLs, because these fluorescent lamps, they basically contain mercury, which is harmful for the environment. So, this graph basically tells you about the timeline of the luminous efficiency, which is measured in lumen per watt. Okay. So, you can see with the time how things have changed. Okay. So, gallium arsenide phosphide for red around 1965 and so on. Okay. And then this is where currently we are. Okay. So, you can see that we are basically having white LED currently. Okay. So, that has become possible because the blue LED was discovered very recently. Okay. Before that, the green and the red was done. Only here the blue LED has been discovered, and then you can mix all these three colors and get your white colors. Okay. So, you can see some of this, that Cree LED bulb is a 7.3 watt bulb and it can give 1250 lumen. So, that is a very high luminous efficiency that has been recorded. So, it is here. Okay. And this Cree, this is also, these two are in lab demonstration. This also hits around 303 lumen per watt, that is the kind of highest till this graph was made. So, LED was initially used for as indicators, red and green, but only when Professors Isamu Akasaki, Hiroshi Amano and Shuji Nakamura, they basically came up with the Indian gallium nitride based blue LEDs that has revolutionized LEDs for the usage in general lighting. Okay. So, the 2014 Nobel Prize in Physics was awarded to them for this marvelous discovery, and because now the blue LED was also available, when you combine the blue LEDs with phosphor, okay, that can give you white light emission from a single chip. So, you have this blue LED, you get the blue light energy, you have phosphors. Okay. So, you will basically get the white light. Okay. So, it is basically you are combining all the three colors are basically available here. Now, different phosphors have different emission characteristics, and thus when combined with the blue light and each other, a high quality light spectrum can be produced. So, what happens typically when a phosphor absorbs a photon of blue, it basically emits a photon of longer wavelength, okay, or lower energy. So, longer wavelength means a yellow or a red, okay, and that when combined with the blue photons can give you the white light, okay, or the different versions of the white light. So, what are the different applications of LEDs in the display industry? The first usage you might have seen in the traffic signals. Because of the high power efficiency and the lower power consumption as compared to the incandescent lamps, okay, LEDs currently replaced all those lamps in traffic signals, and also their lower maintenance cost gives a very big benefit to the councils, okay, and this has also come because of the longer lifetime. Then you might have seen LEDs used in electronic signage and large displays. So, they are basically used for very large area displays which are like several 100 inches diagonal, and the more popular usage of LED has almost reached every home, where it has replaced the CCFL lamps in LCD monitors or displays because they used to contain harmful mercury. Then LEDs can now, because of this, The LCD backlighting is now safe. They are able to provide wider color gamut and better of efficiency. Okay. Also, the LCD displays now have a longer lifetime, fast response time with high power efficiency and longer lifespan, and also they operate below 5 volts. So, the low voltage operation makes them safer and easier for usage. Now, recently a new technology is coming up which is called micro LED technology. So, this basically uses miniaturized LEDs for high resolution displays. So, here they are not doing the backlighting anymore. Okay. They are basically producing the pixels and giving the color on their own. So, they are highly efficient, they are bright, and they have very fast response needed for various applications like projectors, watches and TVs, and they also enable flexible, wearable and stretchable displays by transferring LEDs to different substrates. So, if you do a quick comparison between LCD TV and a LED TV, so typically LED TV has thickness is like minimum 1 inch for LCD TVs. So, LED edge backlit LCD TVs are thinner as compared to the CCFL LCD TVs, and often they are thinner than 1 inch. And the LCDs, they require less power to operate as compared to plasma, but obviously more than the OLED organic LED TVs. Now, if you guys have heard of plasma TVs, so plasma TV technology basically used millions of tiny cells that contained noble gases like neon and xenon, typically sandwiched between glass panels. So, when charged with electricity, the gas turns into plasma and emits ultraviolet light, which causes phosphors to glow in red, green or blue, creating the vibrant high contrast images. Okay, they were quite popular in 2000s, okay, but typically for the high definition home theater experiences, but they were phased out in 2017, roughly that time, when LCD technology could give better image quality while being cheaper, lighter and more energy efficient. So, when people found a better alternative in LCD, plasma simply phased out. Now, LED lit LCD TVs, they consume less power, around 70% as compared to plasma TVs. So, this is where people actually moved away from plasma TVs. Now, what are the sizes of LCDs? Typically 13 to 57 inches, and LEDs can go up to 90 inches, but with continuous technological evolution, now even 100-inch LCD TVs are also not difficult. Typically they have 50,000 to 100,000 hour lifetime, and LED TVs also have something around 100,000 hours lifetime. We understood that wide viewing angle for LCD is a challenge. So, the picture suffers from the side. However, when you look for the LEDs, the brightness and the color on the LCD TVs basically shift noticeably over the screen and depending on the viewing angle. Okay. So, these are basically the LCD lead by the LED TVs, right, LEDs. The last one is the basic technology. So, these are basically layers of liquid crystals where LED TV will be mainly based on the light emitting diodes. So, the last topic we will be covering in this lecture will be the organic light emitting diodes. So, these are slightly different to the semiconductor LEDs. So, here organic LEDs or organic LEDs, they basically have the same principle of electroluminescence which we have seen in the regular LEDs, but the material is different. They use organic thin films with amorphous structures instead of semiconductors. Unlike LEDs, OLEDs do not require crystalline substrate and can be fabricated on large glass substrates or flexible substrates using appropriate processes. Okay. So, this kind of material, like the amorphous organic materials, they have a much lower carrier mobility, typically 5 orders of magnitude lower than the crystalline semiconductors. So, you can understand the driving voltage requirement for OLEDs are significantly higher as compared to LEDs. So, here is the typical structure for a 2-layer OLED. So, you can see you have the transparent anode, the positive electrode, and you have a reflective cathode, okay, which is the negative electrode, and then you have p-type and n-type organic materials giving you that junction. Okay. So, the OLED structure basically consists of thin film of organic layers, which are typically 200 nanometer thick, sandwiched between the anode and the cathode electrodes. So, you can basically use transparent conductors for both anode and cathode if you want to make a transparent display, okay. And if you want to make a display that has got a mirror like appearance, in that case you can have a metallic cathode just like what is shown here. Now, it is quite a challenge in the thin film formation when you go for a large size substrate. So, several different fabrication technology has been produced, such as physical vapor deposition, spin coating, inkjet printing, and also laser assisted patterning for making these OLEDs. So, what are the advantages with OLEDs? Two advantages of OLEDs are low process temperature, and they are compatible with different substrate materials. So, they are very suitable for the flexible displays, and due to their large size fabrication capability, okay, so you can actually make very thin and long thin films or very large size thin films of OLEDs. So, the potential manufacturing cost of OLEDs will be lower than the regular LEDs. So, these are the two advantages in terms of performance and fabrication cost over LEDs. Okay. So, in principle, there is a high chance that OLEDs in future may replace the LEDs in some of the applications, as they are both dependent on the same principle, that is electroluminescence. So, OLEDs are widely used for display applications such as TVs and mobile phones, okay, and OLEDs can also be used in general lighting applications, something like general illumination. Okay. However, OLEDs have some issues, and we will talk about it very briefly, which is called burn-in issue. So, for a prolonged static image, there is an issue with the OLEDs, that there is a ghost like impression that comes on the screen, and that is why for static images, okay, or like for images which are slowly moving, OLEDs are not preferred. We will go into the details if time permits to describe this particular issue as well. So, OLEDs offer flat large area diffuse lighting, unlike LEDs, which are basically point sources with directional emission. So, there are different applications of OLEDs as well when you compare it to LEDs. So, let us make a final comparison between LCD, LEDs and OLEDs. So, when you compare these three, it is important to consider the different advantages of each of these technology offer. So, we understood that LCD screens are the most affordable option of these three, and they are very well suited for applications that do not require a lot of pixel density or color reproduction. LED screens, on the other hand, can offer higher resolution than LCDs and achieve better contrast ratios due to their backlighting system. Okay. On the other hand, OLED displays have an even higher resolution than LED displays, as well as they have very good black levels. So, you get very good contrast ratio and very good wide angle viewing as well. So, next time before purchasing a television, consider your specific needs when you choose between these two technologies and make a wise decision. Okay. So, with that we will conclude this lecture, and if you have got any query, you can drop an email to this particular email address mentioning the course name on the subject line. Thank you.